All right, so this question is in the second review packet, and it's number 4. So in this case, we're actually looking at a function, but it's important to remember what this function is. The function that we see here is actually f prime of x, which we should also think of as the slope of f of x, right? So what we're actually seeing is a model of the slope of our f of x function. So the first letter here, A, is asking us to find the critical numbers. And remember, our critical numbers are any place. A critical number is going to be anywhere where f prime of that number is equal to 0 or is undefined. So in this case, we're looking at a graph of the f prime of x function, and we can actually see exactly where f prime of x is equal to 0, and that's at these 4 points. So the critical values are going to be at x equals, we've got -2, 0, 1, and 4. So those would be my critical numbers. On what interval, if any, is f increasing? So we're seeing the slope of f, and I want to know on what interval is the original function f increasing. So remember, this is showing us slope. So from -∞ to -2, the slope function is negative, meaning f of x is decreasing this whole time because it has a negative slope. But then at -2, it begins increasing, and so the slope is positive this whole time here. So our function is going to be increasing anywhere that the slope is positive, because that's the only way for something to increase, if its slope is positive. So the question really is, where is the slope of this function positive? All right, so we've got a positive slope from -2 to 0, and we've also got a positive slope from 1 to 4. So the function is increasing. F is increasing on -2 to 0, and also from 1 to 4. And that's because, so that we're asked to justify, and that's because f prime is positive. So that indicates that the slope of f of x is positive over that interval as well. And finally, C, at what values of x does f have any local minimum? So if you take a look at what a local minimum would look like, if I've got a function like this one here, I would say that I've got a local minimum there and a local minimum there. And that's because the slope of that function was decreasing and then begins increasing. And again here, decreasing and then increasing. So if I'm talking about slope, that's a negative slope and then a positive slope. So any place where I've got a negative slope over here and a positive slope over there is going to be a local minimum. So let's just take a look at where our slopes are negative and positive. We've got a negative slope here, positive slope there, negative slope there, positive slope there, negative slope there. So we'll look for all the places where our slope goes from being negative to being positive, and that's going to be here and here. So I would say f has local minimums at x equals -2 and 1. And that's because f of x changes from negative to positive at those values. Okay, so let's do another example. This is number 6 from that second review packet. So this time we're asked to find an absolute maximum and minimum of a given function. We can't see it, so now we just have the equation. So we're going to have to do the work to get to see that g prime function that the last problem was showing us. So we need to know what g prime of t is. So we need to take the derivative, and that's going to be 6t minus 2. Okay. So we should consider the possibility that maybe this function is going to have a discontinuity over the interval that we're talking about. So we're talking about going from -2 to 2. Will this function or its derivative function be continuous that whole time? And the answer is yes, because it's a polynomial. So we're covered there. It's something we should consider. So what we want to find now are critical points. And so what we need to do is set g of t, or g prime of t, equal to 0. So when is 6t minus 2? 0. Well, that's going to be at 1/3. All right, so we've got one critical point. But we should also consider the endpoints of this interval, right? Because we're asked to evaluate over this interval the absolute maximum and the absolute minimum. So it is possible that at x equals -2, that's the lowest or the highest point. And at x equals 2, that's the lowest or the highest point. So we only have one critical value, but we do actually have to consider the endpoints as well. So we're going to need to find the position of g of t, not of g prime of t, but of g of t at -2 and at 1/3 and at 2. All right, so I've plugged those in there. Ooh, I've actually got a mistake in our signs. These should all be subtraction signs. That's going to be an issue. Okay, so just to save time, let's go ahead here and calculate this. So g of -2 is going to be 17. And then g of 1/3, okay, so this is a 9th, but this is 3 times a 9th, so that's a 1/3 minus 2/3 plus 1. So that's going to be 2/3. And then we have g of 2, so that's 3 times 4 minus plus 1. Okay, so that's 9 there. So we have all these values of our g of t function now, and we can just try to figure out from this where is the absolute highest and absolute lowest point of our function. Well, the largest of any of these values is 17. So I'm going to say that my absolute maximum is at x equals -2. Okay, so g of -2 equals 17 is absolute max. And the lowest of these points is 2/3. That's the smallest value. So, and f of 1/3 equals 2/3 is the absolute minimum. All right, the last problem from the second review packet that we're going to do is another optimization question, which continues to use this idea of a first derivative and second derivative test. So a box with a square base and an open top must have a volume of 12 cubic feet. So I'm going to sketch it. Square base, so those two lengths are the same. The top is open. All right, so this distance here is the same as that distance because the base is square, but the height could be different. All right, and the top is open. So I'm just going to shade the sides. Okay. The volume is 12 cubic feet, and we're asked what dimensions should it have to minimize the amount of material used. So the thing that we are optimizing, or minimizing in this case, is surface area, because we're trying to minimize material used to build the box. But we know the volume. So in this case, the volume, which is equal to length times width times height, is going to be equal to x times y when we use the values that we've plugged in there, or in other words, x squared y. Okay? But when we talk about surface area, which is the thing that we are going to be minimizing, surface area is going to be equal to the sum of the areas of all of the sides that make up this box. So we've got the 4 sides, which are all identical. We've got this side here, and then the side on that side and that side that you can't see in this picture. Those have an area of x times y, because those are the dimensions of each of those sides. And because there are 4 of them, we'll say 4xy plus, but there's another side as well. The top is open, so there's no material being used there, but on the bottom of the box there is material, and the area of that base is x times x, so plus x squared. So now we have a function that represents surface area, but unfortunately it's got 2 variables. So what I want to do is have this all be a function of x. So what I'm going to do in this case is find out what x, or what y is rather, in terms of x, using the volume formula, because we know that the volume has to be 12. So I can use that to get y alone. And now instead of saying y, I can say 12 over x squared. So I'll say surface area is equal to 4 times x times 12 over x squared plus x squared. And I'll make that look a little nicer here. Okay, so now we have an expression that represents the surface area of this box in terms of the length of the base. But what I want is an expression that discusses the change in this surface area. So if I'm talking about the change in surface area, what I actually want is the derivative of that surface area function. So I'll go ahead and use the power rule here, and a good way to think about 48 over x in this case would be to write it as 48x to the negative 1, otherwise you're using a quotient rule, so let's just try to be efficient if we can. And I'm going to move the x squared term to the front, so we have 2x comes from the derivative of x squared, and then the derivative of 48x to the negative 1 is going to be negative 48x to the negative 2. Now this is something I could rewrite a little bit nicer, because this is the same as 2x minus 48 over x squared, and if I want this all to be over the same denominator, which I'm going to want in a minute, then I'm going to rewrite this as 2x times x squared minus 48 all over x squared, and so I could just write this as 2x cubed minus 48 over x squared. So this is the derivative of my surface area function, or in other words, this function tells me how that surface area is changing at each value for the length of the base. Okay, so what I want to know is the critical point, or any critical points that that change has, because I want to know when is that surface area changing from negative to positive, so, or from positive to negative. So let's find the critical values of that function. So the critical values are going to happen anywhere that the derivative is equal to 0, as we've discussed in the other problems here, or any place where the derivative of surface area does not exist. Okay, so any place that those two criteria are met. Well, this surface area function is not going to exist if x is 0, because 0 is in the denominator. So I'll say in that case, x equals 0 is a critical value. And in the case of surface area, that's going to be when 2x cubed minus 48 is equal to 0. So I'll go ahead and solve that. X is equal to the cubed root of 24. So I'm going to make a number line, and on that number line I'm going to put 0 and the cubed root of 24, because those are the critical values we're going to be discussing here. So let's think about the question then. We're trying to minimize the amount of material used. So what we want to find out is, as we're changing x, when are the values of x that cause us to have less and less surface area, until we eventually hit a point where it's starting to change to be more and more surface area. So I want to find a point where that change is going from negative to positive. That's what I'm looking for here. I don't need to test values less than 0, because that doesn't make any sense within the context of this problem. I can't have a negative length for my base. So I don't need to worry about that. I'm just going to test in these intervals here. One number that I know I could test in this range here would be 1, because 1 is certainly less than the cubed root of 24. So I'm going to go ahead and plug in 1 to that s prime function, or surface area derivative, and if I put a 1 there, this is going to be 2, and 2 minus 48 is going to be a negative value divided by 1, so that would be a negative number. And then I'm going to test a number in this range, a number that's certainly greater than the cubed root of 24, like for example 3. I know that 3 is greater because 3 cubed is 27, which is larger than 24, so let's plug in a 3. 3 cubed is 27, which times 2 is 54, and 54 minus 48 would be positive. Divided by a positive number, we would have a positive value. So I found a point where my surface area is decreasing. I'm getting less and less surface area, which is great for us, but then right here, at x equals the cubed root of 24, that surface area switches to start to increase. So this is the critical value we're talking about. So we'll say, therefore, I guess I'll put it here because this is my space, the dimensions of the box when x equals the cubed root of 24. And what would those dimensions be? They are, well, the length is the cubed root of 24 by, I suppose I should use feet, by the width, which would also be the cubed root of 24 feet, by what would the height be? So let's go back to this function here. If x is the cubed root of 24, then what is y? Well, it's 12 over the cubed root of 24. So I'm just going to say 12 over the cubed root of 24 feet. So that's the answer. That right there is the dimensions of this box that would give us the least amount of material. And our justification is that the first derivative test shows us that the derivative of surface area is less than 0 on this interval, and the derivative of surface area is greater than 0 on this interval. So that indicates that x equals the cubed root of 24 is an absolute minimum.